is Daniela Leitner. My primary job here in the lab is this machinery that you see behind me, which is called the ReAccelerator. And as you might guess from its name, its primary idea is to reaccelerate the rare isotopes that we produce here at the lab. You can see here the project is progressing fast. Also, we are in commissioning phase, but its first stage will come into operation in 2012. So the rare isotopes coming from the cyclotron facility are traveling very fast when they are produced. There's many experiments that can use this fast isotopes, but there are also many experiments that need the ions at a very precise energy. So what we do is we bring the rare isotopes through a gas cell and slow them down to almost thermal speed, so completely stop them. But now they are way too slow for nuclear astrophysics experiments. And so the next step is to reaccelerate them, and that's what happens in this machinery. It's the first step of this process is starting right here in the EBIT ion source. This is a charge breeder. So we take these rare isotopes and we strip many electrons off of them in order to make them highly charged ions. And why do we do that? When they are highly charged, the accelerator process is much more efficient because it's multiplied by the charge. So by going from 1+ to n+, you can make this accelerator much shorter and more cost effective. The ReAccelerator is a linear accelerator. So if you have seen videos from the lab before, you have seen cyclotrons where the ions accelerate as they go in circles. Here they are accelerated as they go straight. And as they come out of the EBIT source, they travel this way, can get mass separated to make a clean beam out of the ions again, and then go through this machinery and go to the first accelerator structure, which is called a radio frequency quadrupole. And in this section, the ions are actually punched to small pieces and then accelerated to a speed of 6,700 miles per second, or 0.6 MeV per nucleon. So behind me now you see the first two modules of the superconducting LINAC structure, where the ions coming from the RFQ at about 3.6% of the speed of light get injected into the superconducting LINAC section that you see behind me, and there they get further accelerated to the final energy that is required by the experiment. So inside here we have small acceleration gaps that we can precisely tune independently from each other, and that means that we can control the energy of the final beam very precisely. So as I said before, that the structure inside is superconducting, that it means that all those cavities are immersed in liquid helium. They run at 4.5 Kelvin or minus 452 Fahrenheit. So we have liquid helium inside these modules. And why do we do that? We do that because by immersing the accelerator structure into liquid helium, the accelerator process is more energy efficient, and the structure can be built much more compact. So the ReAccelerator facility uses the same technology as the FRIP LINAC, which is slated to be coming online in 2018. And one of the missions of the ReAccelerator is actually to prototype those cavity structures for the FRIP facility, so that we get experience and operating experience with these new structures.